All right, let's plunge headfirst into some seriously heavy stuff. We're talking black holes today. You know, you sent us this incredible paper by Stephen Hawking and Roger Penrose, The Singularities of Gravitational Collapse in Cosmology from back in 1970.
Yeah,
And wow, this thing was a total game changer.
it really was. This paper, it helped us grasp how these cosmic giants could actually form in the universe.
So what exactly did they figure out? Like, did they come up with a recipe for actually making a black hole?
Not a recipe exactly, but they did uncover some fundamental truths about gravity.
Okay.
They realized that under certain conditions, gravity could become so strong that it causes like a runaway collapse, like a cosmic implosion.
Okay, so I'm picturing like a building just collapsing in on itself.
Yeah.
Is that kind of on the right track?
That's a great image. Like imagine that building being squeezed from all sides by an irresistible force.
Okay.
That's the kind of power we're talking about with these gravitational collapses.
Wow.
And they happen all over the universe in different ways.
So like dying stars imploding into black holes?
Exactly. That's one way it could happen.
Yeah.
But there's also the possibility of entire galaxies spiraling into supermassive black holes at their centers.
Whoa, now that's just terrifying. But how do we even know these things exist? I mean, we can't actually see them.
Well, we can't see them directly, no, because light can't escape their intense gravity.
Right.
But there's this crucial concept called a trapped surface that Hawking and Penrose introduced.
Okay.
Picture a boundary in space where gravity is so strong that nothing, not even light, can escape.
Oh, okay. So once you cross that line, you're basically toast.
Pretty much, yeah. That trapped surface is essentially the point of no return.
Right.
What we call the event horizon of a black hole.
Okay.
And what's even more mind-blowing is that Hawking and Penrose show that these trapped surfaces could form even in universes that weren't open.
Hold on. Open universes. Are we talking about like the shape of the universe here?
Yes. For a while, physicists thought that these trapped surfaces, and therefore black holes, could only form in universes that were shaped like a saddle, constantly expanding outward.
Okay.
But this paper showed that that wasn't necessarily the case.
So black holes are even more likely to exist than we previously thought. Double yikes. Okay, but what about the stuff inside the black hole? What's at the very center?
That's where we get to the real mystery singularities.
Singularities. I feel like I've heard that word in a sci-fi movie or something.
Yeah.
What are they exactly?
Imagine this. A singularity is a point where all the matter in a black hole gets squeezed into an infinitely tiny space. Imagine crushing the entire Earth into a point smaller than a pinhead.
Okay, my brain hurts just thinking about that.
Yeah.
So these singularities, are they basically like the ultimate cosmic mystery zone? But how do we even know they exist if physics can't explain them?
That's the brilliance of this paper. Really, Hawking and Penrose, they didn't try to describe what happens inside a singularity.
Right.
They focused on proving that they must exist under certain conditions.
So we know they're out there, but we have no idea what's going on inside them.
Exactly. And that's what makes them so fascinating and frustrating at the same time.
Yeah.
One of the key assumptions they used to prove their existence was that gravity is always attractive.
Right. Makes sense. Gravity pulls things together. It never pushes them apart.
Exactly. And there's something called the energy condition that ensures this attractive nature of gravity.
Okay.
And it holds true in Einstein's theory of relativity and some other theories too.
Yeah.
But here's where it gets interesting.
Okay.
There are some theories, like the Hoyle-Narlikar theory, where a C field introduces negative energy.
Negative energy, so like anti-gravity.
Kind of.
Yeah.
And that can mess with the whole gravity is always attractive idea.
Right.
But those are the exceptions, not the rule.
Okay.
So under most circumstances, gravity's pull reigns supreme.
Yeah.
And these singularities are pretty much unavoidable.
So how did Hawking and Penrose actually prove that these things exist?
Well, their paper lays out 3 specific situations that pretty much guarantee that a singularity will show up.
Okay, let's hear them. What are these cosmic clues that point to these mind-boggling singularities?
The first one is the existence of a trapped surface, like we talked about earlier.
Okay.
Basically, a black hole forming.
All right.
The second scenario is a spatially closed universe.
So if the universe is shaped more like a sphere than a saddle, it could eventually collapse back on itself, creating a singularity.
Exactly. That's what we call the Big Crunch scenario.
Okay.
The third situation is where a point's past light cone starts converging again.
Past light cone. I'm not sure I'm following you there.
Imagine you're standing somewhere, and light rays are traveling towards you from all directions, forming a cone shape with you at the tip.
Okay.
Now imagine following those light rays back in time toward their source.
Sure.
If there's enough matter in the universe, those rays would actually start bending inward due to gravity.
So instead of a cone expanding outward, it's like a cone narrowing inward as you go further back in time.
Exactly. And that convergence indicates a past trapped set,
Okay.
meaning a singularity had to exist in the past.
Wow, so this is all connected to what we can actually observe in the universe.
Absolutely. Think about the cosmic microwave background radiation.
Okay.
You know, that faint afterglow of the Big Bang.
Right.
It's everywhere we look.
Yeah.
The fact that it's so uniform suggests there was enough matter in the early universe to cause this light cone convergence, pointing back to a singularity at the very beginning of everything.
Okay, now my brain is really starting to hurt.
Yeah,
But this is seriously fascinating stuff.
it is.
So this paper isn't just about black holes, it also connects to the Big Bang itself.
Exactly. And that's what we're going to dig into next.
Yeah.
So what's fascinating is this paper, it actually laid the foundation for how we understand the Big Bang. It suggests that the universe as we know it actually had a beginning,
Okay.
that all the matter and energy we see today
Yeah.
were once compressed into this incredibly tiny point, a singularity.
So you're saying the Big Bang itself started with a singularity,
Yeah.
and that's connected to what we were just talking about with black holes.
Exactly. Think about that converging light cone idea.
Okay.
If we apply that to the whole universe, it points to a point in the past where everything was packed together
Yeah.
so tightly
Yeah.
that even light was trapped.
Wow.
It's like running the cosmic movie in reverse. Everything kind of traces back to a single point,
Okay.
the Big Bang singularity.
Whoa. Okay, so this paper isn't just about some weird things happening inside black holes.
Right.
It's about the origin of the entire universe.
Exactly.
But how can we be so sure about any of this if singularities are these places where, like, the laws of physics break down?
That's a great question. And to be honest, it's something that still keeps physicists up at night.
Yeah.
The truth is, our current theories, they just aren't equipped to describe what happens at a singularity. It's like, imagine trying to understand the ocean depths
Yeah.
with only a shallow water diving suit, you know. We need better tools.
Right. Okay, so it's like we need a whole new set of physics
Yeah.
to even begin to tackle this problem.
Exactly. And that's where theories like quantum gravity come in.
Okay.
They try to kind of merge Einstein's theory of general relativity,
Yeah.
which is great for describing big stuff like stars and galaxies with quantum mechanics,
Oh,
which explains the tiny world of atoms and particles.
right. So it's like trying to find this single language
Yeah,
that can describe both the vastness of black holes and the weirdness of quantum particles.
precisely. If we can crack the code of quantum gravity,
Yeah.
it might finally give us the tools to peek inside a singularity.
Oh.
But for now,
Yeah.
it remains one of the biggest unsolved mysteries in physics.
Okay, that's kind of unsettling, but also really exciting.
It is, yeah.
So we've got these singularities that seem to defy our understanding.
Yeah.
But Hawking and Penrose, they didn't just say, hey, these things exist and we don't know what they are. Right. They actually found ways to prove their existence.
Right. Remember those 3 scenarios we talked about?
Yeah.
They were like cosmic breadcrumbs,
Mm.
leading us to the inescapable conclusion that singularities are a real part of our universe.
Okay.
And one of those scenarios, that converging past light cone,
Right.
it directly relates to what we can observe in the cosmos today.
You mean the cosmic microwave background radiation?
Yeah.
That faint echo of the Big Bang?
That's the one.
Yeah.
The fact that it's so uniform across the sky
Yeah.
tells us that the early universe was incredibly dense. Dense enough to cause that light cone convergence we talked about. And that points right back to a singularity at the moment of the Big Bang.
So this radiation, it's like a cosmic fingerprint
Yeah,
confirming what Hawking and Penrose predicted.
exactly. It's a piece of observational evidence that supports their theoretical work.
That's pretty amazing. So what are some of the other key takeaways from this deep dive? What should we really remember about Hawking and Penrose's work?
I think the biggest takeaway is that singularities are probably unavoidable features of our universe. Whether we're talking about black holes
Right, yeah.
or the Big Bang itself.
Yeah.
These points of infinite density,
Yeah, okay.
they seem to be woven into the very fabric of space-time.
And these singularities, they're not just mind-boggling, but they also challenge our understanding of physics to its core.
Absolutely. They're like cosmic question marks, pushing us to develop new theories
Yeah.
and explore uncharted territories in physics.
It's like they're saying, hey, we know some stuff,
Yeah.
but there's a whole lot more out there that we don't understand.
Exactly. And that's what makes this paper so important.
Yeah.
It doesn't just tell us what we know.
Right.
It also points us towards what we still need to figure out.
So this paper, even though it's over 50 years old,
I know, right?
it's still incredibly relevant today.
It really is.
It sparked a whole new way of thinking about the universe and laid the groundwork for so much research that's still ongoing.
Absolutely. It's a classic example of how scientific progress builds upon the work of those who came before.
But this journey of understanding the universe, it doesn't end with this paper.
No.
There's so much more out there to explore, and we can't wait to dive into it. Okay, so we've really explored these mind-blowing concepts of trapped surfaces, singularities, and the Big Bang, and it's all thanks to this groundbreaking paper by Hawking and Penrose.
Yeah.
It's just incredible how they connected these seemingly separate ideas, right? And really revealed this deeper understanding of the universe.
It really is. It's a testament to their genius.
Yeah.
They took these really complex mathematical concepts,
Right.
and they showed how they have real observable consequences for the universe that we live in.
Yeah, and one of the most compelling pieces of evidence, as you mentioned, is the cosmic microwave background radiation, right? It's like this faint echo of the Big Bang, just whispering secrets from the very beginning of time.
Exactly. And the paper actually goes into some detail about how this radiation supports their ideas. They talk about something called the optical depth of the universe,
Okay.
which sounds pretty technical.
Yeah, optical depth, that's definitely not a phrase I use every day.
Right.
Can you break that down for us? What does that even mean?
Sure. So imagine you're shining a flashlight beam through a fog.
The
thicker the fog,
Yeah,
the harder it is for that light to get through.
right.
That's kind of like optical depth.
Okay.
It's a measure of how much stuff light has to pass through.
So a higher optical depth means more stuff for the light to interact with.
Exactly. And in the early universe, that stuff was mostly a hot, dense soup of particles. Hawking and Penrose used a concept called Thomson scattering, which basically describes how light bounces off of particles.
Okay.
By figuring out how much scattering would have happened in the early universe, they could estimate how dense it must have been.
Okay, so they're basically using the behavior of light to work backward and figure out what the early universe was like.
Yeah.
It's like cosmic detective work.
It really is.
Yeah.
And what they found is that the optical depth of the early universe seems to have been high enough
Okay.
to support that idea of light cone convergence we talked about earlier.
So even though we can't directly observe the singularity at the Big Bang,
Right.
we can kind of see its fingerprints in the way that light behaves.
Precisely. The cosmic microwave background radiation, it provides strong evidence
Yeah.
that the early universe was dense enough for this convergence to happen, which points back to a singularity at the very beginning.
It's mind-blowing to think that a paper written, over 50 years ago could have such profound implications for our understanding of the universe.
It is, yeah.
What a legacy.
Absolutely. Hawking and Penrose's work was truly groundbreaking.
Yeah.
They opened up new avenues of research,
Right.
and they laid the foundation for our modern understanding of cosmology.
So as we wrap up this deep dive,
Yeah.
what's the biggest takeaway for you? What's the one thing you hope our listeners walk away pondering?
I think it's the realization that the universe is full of mysteries. And even though we've come a long way in understanding them,
Yeah.
there's still so much more to discover.
Yeah.
Papers like this one remind us that science is a journey, not a destination.
It's a journey that requires curiosity, a willingness to challenge our assumptions,
Yes.
and a sense of wonder at the vastness and complexity of the cosmos.
Absolutely.
And who knows, maybe someday you, our listener, will be the one making the next groundbreaking discovery.
I hope so.
So keep exploring, keep questioning, and keep diving deep into the mysteries of the universe.
Yeah.
Thanks for joining us on this incredible journey.